Hello everyone. Today we're going to conduct experiment on young modulus. So we're going to confirm young modulus for a particular material. And the material we have chosen today is a wooden material called a metal rule. So young modulus is a measure of stiffness of a material. And for a wooden material, if you go online, you can search for so many young modulus of different type of material. You'll be able to capture the stiffness of different setup. This is called a cantilever setup. As you can see, this is how it looks. The whole of it is cantilever setup. So we have a horizontal meter rule and we have a vertical meter rule. Both are of the same length, 100 centimeter. So and we have our weight of 80 grams. We have our weighing balance, which we're going to test to ensure the accuracy of our weight. So our weight is 80 grams, as you can see. So as I have mentioned, all you need to conduct this experiment is 2 meter rule, the reference meter rule, 2 G-clamp to fix your meter rule at a certain position, and then you need a weighing balance to weigh your load, and then you need a stopwatch. So in this experiment, we chose to use a digital stopwatch in order to avoid parallax and zero error. So this is iteration of 95. Then we now set it to oscillate. We have already noted the initial position of the meter rule before attaching our load. Here it was on 47.5. Then we'll attach our load and extend it back to these 47.5. Then the moment, then after the count of 3, I will release it, and at the same time I will start my stopwatch. 1, 2, 3, start. 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We stop. This will be the period, the time recorded. And we'll do it twice and take average. And then we'll now divide the average by 20 oscillation to record our period. So this is the same procedure that we're going to do for the remaining iterations. Allow it to swing for 20 oscillation. And this is for you to be able to test the strength of that meter rule, because anything you attach load to it and allow it to swing for a certain period of time, that particular body will have some, you'll be able to know the stiffness of that body. Because if the body will easily deform, then by that 20 oscillation, you'll be able to have your deformation. So we'll now take it to 47, the initial length before attaching our load, and then we'll release it and allow it to swing for 20 oscillation. This is 47. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So after 20 oscillation, you remove it and check if it goes back to that 47. You check if it goes back to that 47. If it goes to that 47, you record your length, initial length as 47, and your final length as also what? 47. But if you were able to have some deformation, then you will have to note it. If, for example, initially was 47, and then after attaching our load and allowing it to swing for 20 oscillation, for example, it goes down to 47.5, then we'll say our deformation is 0.5 for that particular length. But as you can see, because our horizontal meter rule is the length displaced is very large, as you can see, it has come back to somewhere close to that 47. We can see the value by bringing it closer. We see it's now exactly on 47.1, which means our deformation is just 0.1. So the next thing to do is to go back and change the length. We're going to pick the same iteration all through our experiment. The first iteration was 5 centimeter. The second one now is to remove our clamp and then reduce the length, move it back to 90. We make sure 90 coincide with the edge of the bench, as you can see. Then we tie our G-clamp back. So now let's look at 90 very well. Does it coincide with the edge of the bench? It does, right? So we have moved, and then we'll move our bench a bit forward. We attach our, and then before we take our second iteration, we'll have to make sure we note our initial length again. When we come back, our initial length now is 46.5, sorry, yeah, 0.5. Then we'll now attach our load and then take it back to that 46.5, and then we will allow it to swing for 20 oscillation again. I'll do it again. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Then we'll stop and check if it goes back. We'll allow it to settle before we check if it goes back to that 46.5. So as you can see, it has settled, but the way it looks, I think we have a bit, we have a very small deformation. It might be maybe 0.1, or it might go back to its initial length. So as you all know, this is just experimenting with a very small load. If the load is bigger than this, we'll definitely be able to have a reasonable deformation. So this is how the experiment will be done for a minimum of 6 length. We have taken iteration of 5. We've started with 95. We can then reduce it to 90, and then next to 85, and then to 80, then 75 to 70, and then 65 minimum. So young modulus define the stiffness of a material. If you go online and search the young modulus of different wooden material, you'll be able to have so many values for different type of wooden material. For example, a redwood will have a certain value. White wood, a different type of wood, will have their own values. So after you're done with that, you will now take the result of this experiment and compare with the young modulus of various wooden material you found online. One will be the theoretical value, and this will be your experimental value. So based on this, you will now compare the value you got from this experiment with those wooden material. The value that fits your result here will be the type of wooden material we're experimenting for. And then you will call this wooden material that particular wood from your literature. So as you can see, it has been paved with color, so we can't really identify the type of wood is within. So this is the end of the experiment, and I hope you learned something.